Hello everyone, welcome back to my YouTube channel. Today I am going to show you another tutorial of Fluent Meshing. Here we have shell and tube heat exchanger in which cold fluid is passing on the tube side and the hot fluid is passing on the shell side. And we want to use Fluent Meshing for its meshing. For Fluent Meshing you always need shared topology. Therefore we will go to the workbench and here we have the option for sharing our topology. Here you can see all those regions which could be shared and it looks fine. We can hit the screen tick and we have shared all those regions. For meshing in Fluent, we also have to define our boundary names in here. I want to use this surface as the inlet for the hot fluid. Therefore, I will go to this group and create name selection. There is a shortcut for the Control G. I can give it a name inlet underscore hot. Similarly, this one Control G and it is our outlet underscore hot for hot fluid. I want to do it for counter current. You can select over here Control G. I can say inlet for the cold fluid. And also this one definitely should be outlet for cold fluid. So I want to define name for this surface so that I can define the convection boundary condition. Control G and I can call it convection. We have defined our boundary name. We have created shared topology. Now we can go to the Fluent Meshing. I have opened Fluent Meshing. In that you have to go all these steps one by one. First, to the import geometry, you have to import geometry manually. It will take maybe a couple of seconds. Our geometry has been imported. Now let's move to the local sizing. They are asking if we want to add local sizing. I don't see any special region where we need a special sizing. It is used, for example, at some particular location you need really fine mesh, then you can add local sizing. I did not define any specific region for local sizing. I could say no and update. Then in generate surface mesh, we have to define our maximum and minimum size for our meshing. Fluent show these blocks just to give you an idea. It looks fine, smaller element, because on the solid I want to have approximately 2 elements. It looks good, so I can keep it at 3. And on the bigger size it looks really big. We can reduce it to maybe 1 millimeter. Yeah, that should be the maximum element size. It looks fine. Growth rate 1.2, that's fine. We want to capture the proximity and curvature normal angle 18, that's fine, it is default. If you reduce this angle, your mesh on the curvature will be finer. Actually this one is the angle between the normal of two faces. So it means when you set this angle smaller, it will resolve bigger element and try to reach that angle. Let's keep it 18 and then we will maybe see later how it will change. With this setting we can generate our surface mesh. In Fluent Meshing, surface mesh is the basis which is used for generating volume mesh. Surface mesh has been generated. Now let's move to describe geometry. The geometry consists of a fluid region with no void. Okay, consists of both fluid and solid region and or voids. We don't have any voids, but this one is the correct definition of our geometry. Will you keep opening and extract fluid region? No, we have already defined our fluid. Change our fluid to fluid boundary type from wall to internal? Yes. Do you want to share topology? No, that we have already done. Enable multi-zone meshing? No, we don't need to do that. Multi-zone create problem for the complex geometry and we don't need in this case. Describe geometry. This one is our wall, inlet cold fluid velocity inlet hot velocity outlet, and these are our pressure outlet. Yeah, it looks fine and we can say update our geometry. Create region. Yes, we have two fluid region. Update region. Let's check. Wall solid fluid. This one is not correct actually. I don't remember. What did I call this? Okay, let's see. Update region. Now add boundary layers. Yes, we want to add boundary layers, smooth transition. It is the name of the boundary layer. The method, first let's stick to the smooth transition because I did not calculate the height of first element. So I will stick to the smooth transition. And let's say I want to have 8 layers on the fluid region and on the wall side. Actually, I forgot one thing. I did not define the symmetric region. We have to go back to the space claim and have to define our symmetric region because I am simulating half of the region and it should be symmetric. I am back in the space claim and let's select our walls. This, 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 and this. Anything else? No. Control G, and these are our symmetry. Now we can close this and go back to Fluent Meshing. It will start again. Import geometry. No local sizing. That's good. It is retaining all those settings which we did before. Sizing, min and max sizing. Surface mesh has been generated and all settings have been retained. We can move quickly. Yes, now you can see symmetry has been added. Update boundary, create fluid region, again update region, boundary layers, everything has been retained. Name, and now we want to create mesh. Fill with polyhedron, no, we want to fill with polyhexa with one buffer layer. That is the minimum size and that's the maximum size. Generate the volume mesh. You can see this fluent meshing is pretty straightforward. You don't need to do a lot of things. Most of the things are automated. Just go through those steps and check your geometry, define your boundary region, boundary condition, add your layers, and that's it. Soon we will have our meshing, then I will show you how our mesh will look like. Okay, our mesh has been generated and you can see it has created boundary layers, and if we see inside we would be able to see the hexa mesh hopefully. Yes, we can see. Come here. We need to move a little bit center. Most of the mesh is polymesh. I asked for hexacore, but I think it is unable to fit the hexa element. That's why it has created only polymesh. But it's good enough. One comment: in the solid region, you could see there are only two elements. That is fine because there will be only conduction, which is a linear problem, so there shouldn't be any problem with the one element. But on the fluid side you would need more elements. As you can see over here, we have 8 elements and we should get reasonable results. I am not going to do simulation with this mesh, but in another video I did simulation for this geometry, but for that I did meshing in Ansys Meshing. If you are interested in the simulation, just check out that video. I will provide the link in the description. That's it for today. Thank you for watching and see you in the next video.